Imagine a weapon so sharp it could slice a silk scarf, falling through the air by mere gravity. A blade so resilient it could bend 90 degrees and snap back to its original form without a single fracture. For centuries, the Damascus blade was whispered about in the courts of kings and the heat of crusades as a supernatural entity, a metal forged with dragon's breath or quenched in the blood of stars. But in the year 2006, the myth collided with a terrifying reality under the lens of an electron microscope. Scientists found that these ancient blades didn't just contain high-quality steel. They contained the very building blocks of the future, carbon nanotubes. We are looking at a technological anomaly, a ghost in the machine of history. Today on Wikivedia Plus, we will decode the lost molecular secret of the Damascus Steel and the ancient masters of nanotechnology. Let's dive in. The year is 1191. The sun beats down on the sands of the Levant with an unforgiving intensity. Richard the Lionheart, the formidable king of England, meets Saladin, the sultan of the Ayyubid Empire, in a legendary encounter of mutual respect and hidden power. The European chronicles of the time are filled with a peculiar sense of dread when describing the swords of their adversaries. While Richard boasted of his heavy, straight broadsword, a weapon designed for crushing bone and cleaving through heavy iron plate armor, Saladin drew a different kind of power. He drew a curved, shimmering blade that seemed to hold the reflection of flowing water within its metal. With a casual flick of his wrist, Saladin tossed a silk cushion into the air, and as it descended, the blade whispered through the fabric, splitting it in two without a sound. This was not merely a sword. It was a marvel of engineering that left the Western world in a state of primitive shock. The Europeans saw the water-like pattern on the steel and called it Damascus Steel, but they had no idea that the secret to its power was hidden at the atomic level, deep within the grain of the metal itself. The mystery of this steel did not actually begin in Damascus, but thousands of miles away in the crucible pits of ancient India and the northern regions of Sri Lanka. There, artisans were producing what would eventually be known as wood steel. This was not the iron smelting process known to the West. These ancient metallurgists would place high-purity iron ore, charcoal, and secret organic additives such as specific types of wood, glass, and even the leaves of rare plants into small clay crucibles. They would seal these containers airtight and bury them in a furnace for days at a time, maintaining a precise, high temperature. This long, slow cooking process allowed the carbon from the organic materials to migrate deep into the iron, creating a unique high-carbon alloy. These small ingots, no larger than a man's palm, became the most valuable commodity on the Silk Road. They were traded through the Persian empires and reached the master smiths of Damascus, who were the only ones who knew how to unlock the hidden potential within the wood's ore. For nearly 500 years, the recipe for forging these blades remained the world's most guarded military secret. It was the equivalent of a nuclear program in the Middle Ages. If a king possessed a Damascus blade, he possessed an edge that no other army could match. But by the 18th century, the world changed. The secret simply vanished. Historians have debated for centuries why the production stopped. Some believe the specific iron ore in India, which contained trace elements of vanadium and chromium, had simply run dry. Others suggest that the master blacksmiths, fearing for their safety or wanting to protect their legacy from colonial powers, took their secrets to the grave. For the next 300 years, the greatest scientific minds of the Enlightenment and the Industrial Revolution tried to crack the code. Michael Faraday, the man who gave us electromagnetism, was obsessed with Damascus steel. He spent years in his lab trying to alloy steel to match the ancient blades, but he failed. Jean Robert Brent conducted hundreds of experiments for the Napoleonic Army, hoping to give French soldiers the advantage of the Damascus edge. He also failed. The metal of the ancients had become a lost technology, a silent rebuke to the supposed superiority of modern science. Then came the year 2006. In a laboratory at the Technical University of Dresden, a team of researchers led by Professor Peter Pfäufler decided to subject a genuine 17th century Damascus saber to the ultimate test. They weren't interested in the history. They were interested in the molecules. They took a microscopic sample of the blade and dissolved it in hydrochloric acid to see what would remain. In any standard high-quality steel, the structure would simply break down into its base elements. But as the acid ate away the iron, something extraordinary happened. When they placed the residue under a transmission electron microscope, they didn't see broken metal. They saw long, hollow, perfectly formed cylinders of carbon atoms. They were looking at carbon nanotubes. These are the same structures that modern engineers believe will one day build space elevators and the next generation of supermaterials. But here they were, integrated into the fabric of a weapon forged hundreds of years before the invention of electricity. The shockwaves of this discovery were felt throughout the scientific world. How did a medieval blacksmith, working in a charcoal fire with primitive tools, achieve what the father of electromagnetism could not? The answer lies in what we now call thermomechanical cycling. Through thousands of years of trial and error, the smiths of Damascus had discovered that if they heated the wood steel to a very specific shade of cherry, red a temperature we now know is around 800 degrees Celsius, and hammered it with a particular rhythm, the trace elements in the iron would act as catalysts. These impurities, specifically the vanadium and chromium, forced the carbon atoms to align themselves into long nanotubes. These nanotubes then acted as a protective sheath for the internal nanowires of cementite. Cementite is incredibly hard, but very brittle. However, when it is encased in a carbon nanotube, it becomes flexible and nearly indestructible. The blacksmith was a nano-engineer who used his eyes and his intuition instead of a computer. He didn't know the word atom, but he understood the soul of the metal. This realization forces us to reevaluate our understanding of human progress. We often like to think of history as a straight line of constant improvement, but the Damascus blade is physical proof that knowledge can be lost as easily as it is found. We are living in a peak of technology today, but we are only now catching up to the material science of the 12th century. The Damascus smiths possessed a connection to their materials that was both scientific and spiritual. They didn't just make tools. They manipulated the very fabric of reality at the nanoscale. They reached into the fire and pulled out the future. As we look at these blades today, shimmering in museum displays, we aren't just looking at weapons of war. We are looking at a bridge between eras, a bridge built of carbon, fire, and a level of genius that defies the passage of time. As the echoes of today's story fade back into the archive, we are left once again at the edge of the unknown. Thank you for journeying with us to the fringes of history and science. If these mysteries resonated with you, we invite you to support the channel by liking this video and subscribing to our growing community of seekers. Share this transmission on your social networks. Your curiosity is what keeps these stories alive. We will return soon with another chapter that was never meant to be told. Until our next encounter, stay curious. This is Wikivedia Plus.